Hi, welcome to a theory update on muon g-2. In 2023, the muon g-2 experiment at Fermilab released a new measurement. You can find the reference for the result in the description below. Its potential implications for our understanding of physics beyond the standard model were huge. The quantity that they measured was the anomalous magnetic moment of the muon, or equivalently muon g-2, sometimes written as g-2 with a mu as a subscript. Why was this result potentially so important? Many types of new physics, like supersymmetry, new Higgs bosons, leptoquarks, etc., could first show up as a discrepancy between the measured value of muon g-2 and the value predicted in the standard model. And their measurement of muon g-2 differed from the standard model expectation by 5.1 sigma. More generally, a deviation in muon g-2 from the standard model prediction might be an indication of the existence of previously unknown particles or forces. But even if it agrees with the standard model prediction, it is still important, because then it can be used to constrain or rule out some models of new physics. The 2023 result was expressed in terms of A mu, which is just muon g-2 over 2. It used the first 3 years of the experimental data from the muon g-2 experiment, and it was combined with the result from when the experiment was located at Brookhaven National Laboratory. Here we show the difference between the 2023 measurement and the standard model prediction at that time. On both sides of the first equation, the first term is the experimental result, and the second is the standard model prediction, subtracted off. The numbers in parentheses at the end of each term give that term's uncertainty in the last few digits. In the last line, we have the difference between the two. And we can see that the difference is more than 5 times the uncertainty. The difference between the 2023 Fermilab measurement and the standard model prediction at that time was 5.1 sigma. So, yeah, the difference between observation and prediction was more than 5 sigma, which in particle physics is often taken as a threshold for possibly declaring a discovery of new physics. But there were enough questions about the standard model prediction back then that no discovery was declared. In fact, if we look back at that comparison between observation and the standard model prediction, we see that the uncertainty on the measurement was actually less than the uncertainty on the standard model prediction. Usually, when there's news about a result in particle physics, it's about a new experimental result. And a new result from the muon g-2 experiment at Fermilab using their full dataset is expected on June 3rd. But that's not what we're doing this time. This time we're talking about an update to the standard model prediction. The previous calculation for the standard model prediction of muon g-2 was from 2020. You can find a reference to the paper in the description below. It was produced by the muon g-2 Theory Initiative, a group of over 100 physicists, and the paper was almost 200 pages long and referred to a very large number of previous works. The new standard model prediction is from the same group. Here's the reference, which you can also find in the video description below. It has over 200 authors, and it cites a huge number of previous works. Here, we're just going to give a summary of the updated results. For lots of background information on muon g-2, including what it is, how it's measured, and how new physics can show up in it, check out the mini-series on g-2 of the muon, available on this channel. In particular, you might want to check out the video the value of muon g-2 predicted in the standard model, if you want to understand this video a bit better. Okay, so let's look at what changed between the standard model prediction for g-2 formulated in 2020 and this new prediction that has just come out. Contributions to muon g-2 are written in terms of Feynman diagrams, and they are grouped into three classes depending on the particles in the diagrams. The first group are the quantum electrodynamics, or QED, corrections. These diagrams contain only photons and leptons. They give the largest contribution to muon g-2. Next, we have the electroweak corrections. These are from diagrams that contain W, Z, or Higgs bosons. These make small contributions to muon g-2 because heavy particles in diagrams make for small contributions, and the W, Z, and Higgs are all comparatively heavy. Lastly, we have the hadronic corrections, which are from diagrams that contain quarks and gluons. These contributions have the largest uncertainties, which they impart to muon g-2. To illustrate, we can look at the 2020 standard model prediction for muon g-2 broken down into these pieces. Remember, the numbers in parentheses are the uncertainties on the respective terms. The QED piece is the largest by many orders of magnitude, but it has the smallest uncertainty. The electroweak contributions are the smallest, but have an uncertainty considerably larger than that of the QED contribution. The hadronic contributions, however, have by far the largest uncertainty. In fact, we can see in the total in the last line that the uncertainty on the hadronic contribution basically determines the uncertainty in the prediction for A mu overall. All three of these were updated in the latest calculation. The QED piece got small changes, so did the electroweak. The important changes were in the hadronic contribution, so let's talk about that. So why is the uncertainty on the hadronic contribution so big? The hadronic contribution consists of those diagrams containing quarks and/or gluons. At high energies, we can calculate these diagrams in much the same way as others. But at low energies, quarks and gluons are bound together by the strong force into particles called hadrons. When this happens, the standard calculational techniques don't apply, and the calculations are much more difficult. Those difficult diagrams come in two classes. The first is called the hadronic vacuum polarization diagrams. These are diagrams that contain hadronic processes which are attached to two photon lines. Here, the photon lines are the wavy ones. The second class of diagrams are called hadronic light-by-light scattering diagrams. These diagrams contain hadronic processes attached to four photon lines. Of these, the hadronic vacuum polarization diagrams are the most important, both in terms of size overall and in their uncertainty. There are two calculational techniques for dealing with these difficult diagrams. The first is called lattice QCD, where QCD stands for quantum chromodynamics, the theory of the interactions of quarks and gluons. The second is called data-driven methods. Let's briefly compare them. Lattice QCD is a first principles calculation based on the laws of quantum chromodynamics in the standard model. It is computationally very intensive, but, and this is important, it has seen very big improvements in recent years. On the other hand, in data-driven methods, you don't try to calculate the quantity you want from scratch, as it's too difficult to do. Instead, you relate the quantity you want to other physical things that you can experimentally measure. Then you take measurements of those things and derive from them the quantity that you're actually looking for. So back to those two classes of difficult calculations. Let's see what changed from 2020 to 2025, keeping in mind that of the two, the vacuum polarization diagrams have the larger uncertainty, so they are likely more important to the update of the prediction. We'll start with the light-by-light diagrams. In the prediction in 2020, both lattice QCD and data-driven methods were used. In 2025, they did the same thing but made improvements to both. For the vacuum polarization diagrams in 2020, they used data-driven methods only. In 2025, they used lattice QCD to get the most important contributions. So, why the change? There were two reasons. First, in the data-driven methods, they related the hadronic vacuum polarization diagrams to the process E plus E minus goes to hadrons. This is where a positron and an electron collide and produce hadrons. So they could take measurements of the rates of that process and use it to calculate the vacuum polarization diagrams that they needed. These measurements came from a bunch of different experiments. But there was a bit of an issue with those measurements. In 2020, those measurements of E plus E minus to hadrons were in tension with each other. In other words, they didn't agree with each other as well as they should have. And in 2025, this tension was still not resolved. In fact, it had gotten a bit worse as new data came in. And then there is the second reason. The lattice QCD results got more precise. In 2020, the lattice results could not compete with data-driven methods for the hadronic vacuum polarization contributions. But there have been large improvements in the lattice QCD calculations in the last 5 years. So now, lattice QCD appears to give the more reliable result for the main piece of the hadronic vacuum polarization calculation. So it made sense to switch to using lattice QCD for the main piece of the hadronic vacuum polarization contribution. And since these diagrams were the biggest source of uncertainty in the standard model prediction, this choice is very important to the result. So let's get to the new standard model prediction for muon g-2. Here's their new result broken down into the QED, electroweak, and hadronic contributions, with the total at the bottom. I will note that in this video, I have lumped the two types of hadronic contributions into a single number, while the muon g-2 theory initiative quotes separate numbers. So it's possible that there is a rounding error in the last digit of the hadronic number, and if so, that error is mine. By comparing the uncertainties on the hadronic number and on the total, we can see that, again, the uncertainties on the hadronic contribution basically determine the uncertainty on the total. Let's compare it with the old result. Well, that's a lot of numbers, so let's just look at the important ones side by side. Here, we compare the new and old results for both the total prediction for A mu and for the hadronic component by itself. You can see that from 2020 to 2035, both of these numbers went up by about 223, 224 in the last 3 digits. The change in the total is almost entirely due to the hadronic component. So that's our first conclusion. And let's compare that new prediction to the measured result from the muon g-2 experiment from 2023. The difference between the two is now much reduced. In fact, it's now less than 1 sigma. I am a person who studies physics beyond the standard model, so I'm going to put a sad face here. But this is also an incredible achievement on the part of both the muon g-2 experiment and the muon theory initiative. And This can help in constraining models of new physics, so a happy face is also justified. The discrepancy between the observed and predicted values of muon g-2 has been a long-standing mystery. Is that mystery solved? Not really. Naively, if the measured value of muon g-2, which is expected from the Fermilab experiment very soon, doesn't change much from its current value, this looks like the discrepancy between prediction and observation has essentially disappeared. However, in principle, the lattice QCD and data-driven calculations for the hadronic contributions to A mu should agree. And they don't. So the mystery shifts to understanding why those two numbers are so different. But more immediately, the new and final results from the muon g-2 experiment are expected to be announced on June 3rd. So be sure to check that out.